Okay, so this is Unit 5 in Eltn 132, and we're going to be talking about Karnaugh or Karnaugh maps, depending on the way you pronounce it. Usually it's just abbreviated Kmap. So, like we've been doing with our using Boolean algebra or gate reduction using De Morgan transforms also, kind of the goal of using these this method is to reduce the number of gates in a circuit, to minimize it. So what I've got shown here is some kind of logic circuit. I'm just kind of showing it as a box here, where we have three inputs, A, B, and C, and one output X. I'm not showing the AND gates or the OR gates because I'm treating it kind of generically. But let's say, for example, we've got this truth table, and it's based on some kind of design requirement. Maybe inputs A, B, and C are sensors or switches or whatever it may be, other logic devices. And we've been basically defined all of the output values of X for all of the possible input combinations. So we've got a truth table here. Now what we're going to try to do is reduce this. Rather than build it just with a bunch of gates without thinking about it, we're going to go through a systematic process of reducing the gates to try to optimize the circuit. So basically how Kmaps work is that they look at don't care conditions, where there are redundancies that are unnecessary that we do not need a gate input to define the output. Let me give you an example of where this occurs here. Let's take a look at these two sets of inputs. Okay, A and B are both 1, C is 0. In this case, on this row, A and B are both 1 and C is 1. But you'll notice that the output is 1 or true regardless of what C is. Okay, both A and B. So in any case in this whole map here, where A and B are 1, X is going to be 1. So we don't care what C is. It doesn't matter if it's a 0 or 1, the output is going to be a 1. And so what the Kmap does in a very systematic order is help us identify where the redundancies are and figure out how to eliminate those. So the first step is we're going to create a 8-cell matrix here, 2 by 4. And what each of these rows represent are the inputs A and B. What the vertical cells represent are the value of C for the input. And so that's kind of what this bar represents here. Now, what this is going to do then, all of the ones and zeros that go inside the box are going to be whatever our output values are for each of the input combinations. So the way that these are written is it's a very specific sequence. So we write A is 0 and B is 0, then A is 1, B is 1, and this is where it kind of gets a little funky. We write 1, 1, and 1, 0. So it's not in the binary counting sequence. The reason we do that is we only want one transition of a variable between any two rows or any two columns. So for example, from here we have 0, 0 going to 0, 1. The only thing that's changing is B. That's represented by the right-hand side. Or if we go from this row to this row, B is already 1. The only thing that's changing is A. We can't have two transitions at the same time. C is simple. It's just going to either be 0 or it's going to be 1. So the next thing we're going to do is populate this Kmap. We're going to take the values from this truth table and map them over to this set of 8 cells here. So the way that we're going to do this is kind of read these numbers off from A, B, and C, and then figure out what the output is based on here. So for example, in this case, A is 0, B is 0, that's what those two represent, and C is 0. So that's going to be this first row, and the output is 0, so we end up writing a 0 in that cell. The next cell is 0, 0, 1. So that would be this cell here, and we write that, and because X is 1, we write a 1 here. So all of the cells are actually going to be filled with the values of X. That's all we're doing here. The next one is 0, 1, 0. Okay, and that's over here, 0, 1, 0, and that's a 1. So we'll put a 1 in there. The next is 0, 1, 1, and that's a 1. Now here we got to be careful. We're jumping a little bit. we're going to 1, 1, 0. Where is that? Well, it's in this row here, 1, 1, 0. So that's a 1. And 1, 1, 1, A, B, and C, 1, 1, 1, is the same as the bottom one here. So that's a 1. Then we have 1, 0, 0, which is shown right here. That's a 0, 1, 0, 0. And finally, A is 1, B is 0, C is 1. That'd be 1, 0, 1, A, B, and C, and that's a 0. So that's kind of the first step, is filling in the cells for the Kmap. So the next step, once we've populated the Kmap, is to try to locate groups of ones that are adjacent to each other, either in powers of 2, 4, or 8. They refer to these as prime implicants. Now, adjacency, I kind of have to define. I realized I should have probably explained this ahead of time. But let me give you examples of what I mean by adjacency of the cells. I'm going to start with groups of 2. If we have 2 cells that are right next to each other, those are considered adjacent. If I have 2 cells that are side by side, those are also considered adjacent. You can kind of draw a little circle around them to show that they are. What gets a little weird here is that if we have a cell here and a cell here that are both 1, they are also adjacent. You can draw a line like that. We can also group groups of 4. So for example, if we have 1, 1, 1, 1, those could be all grouped together as a single term. And I'll explain what we do with that eventually. We could also have 1, 1, 1, 1 like that. And what's kind of weird also is we could have 1, 1, and 1, 1, and they're literally mapped like that. So top and bottom. So you have to kind of think of it almost like as a piece of paper that's folded around like that and folded around like that as far as determining adjacency. Now, if that isn't clear, I think as I go through the rest of this example, it'll make a little more sense. So let's take a look at our example here. Or do we have any cells that are adjacent? Let's start with the groups of 4, for example. And yes, we've got these 4 here that are all grouped together. Are there any others? And the answer is yes. These 2 also can be grouped together like that. Okay, so we've grouped all of those values together. Now let's see what that means. So let's take a look at these cells where we have an adjacency. Okay, so the address of that would be, or we think of the inputs, 0, 0, 1 and 0, 1, 1. Now, what we're looking at is that as we're transitioning between those 2 cells, as we're going from that cell to that cell, we're trying to see what is changing and what's staying the same. And if something stays the same, we're going to write that value down as one of the actual input values. So let's start with A and B. If we go from that row to that row, A is what? It stays at 0. So what we're going to do is write A0 as one of the possible input combinations. Now, how about B? Well, it's transitioning from 0 to 1. And what that equates to is that don't care condition. So we throw out B. If we transition from a 0 to a 1 or a 1 to 0, we get rid of it. Now, how about C? If we go from that row to that row, does C change? The answer is no. But what is the value of C? It's 1. So we write that then as C. A0 C. So that's one of the terms in our circuit. Okay? So again, we're looking for transitions. We're going between from top to bottom and left to right. In this case, we're only going from top to bottom because that's the only way that it's transitioning here. So again, because A is 0 and it isn't changing, we're writing that as A0. B is transitioning from a 0 to a 1, so we throw it out. It's a don't care. C, however, is a 1 and it doesn't change, going from the top to the bottom. So anytime you have two of these cells grouped together, it is going to give you two terms, always. So if you ended up with three terms, something's wrong there. Now, let's take a look at the next set of ones. Okay, so we have 4 ones here that are grouped together. So I'm going to group them. I'm going to mark, by the way, getting colored pencils or pens is really handy when doing these problems because there's a lot going on. We're going to do the same thing. We're going to look at the changes now. In this case, because we've got 2 columns and 2 rows, we have to look at what's going on in both directions. So let's take a look here. When we're going from top to bottom, A is transitioning from 0 to 1. So what do? We throw it out. Okay? B is not transitioning. It's staying as 1. So we're going to write that as a term here, B. Now, how about going from left to right? Well, for both of those sets, C is transitioning from 0 to 1. So what does that mean? We have to throw it out. There is no C term. So, now that we've done this process, we've grouped the ones, we've identified what the values are, we can now write the whole equation. X equals A naught, C, or B. So now that we have that equation, we can draw the circuit with gates. So we have input A here, we have input B, and input C. Now right away we can see that A is inverted, so we have to add an inverter there to create the A naught term. And it's ANDed with C. So I'm going to bring this up here and AND those two terms together. Now B needs to be ORed with that. So I'm going to draw this all the way over here, and we're going to OR those terms together. And that should be our final circuit. So if we just kind of blindly tried to design the circuit based on what we have up on the truth table, we would have had a 1, 2, 3, 4, 5 input OR gate with all sorts of other gates trying to make the logic work. But in this case, by grouping these together and finding the redundancies here, okay, I left that guy off there, we're able to reduce the circuit substantially. Now, I want to show a couple other ways that we could look at or examples with this 8-input Kmap to kind of get an idea of how the grouping works. So let me give a what if here. What if when we were mapping this out, the output 1, 0, 1, which is over here, was actually a 1 also? Well, then this would be a 1 here. And let's take a look at the grouping that we'd have then. We could go and group these 4 here, and we always want to start with the largest possible numbers to group. If everything was a 1, we'd group the whole thing and it would just be a wire. There'd be no logic in it at all. But we want to start with the largest number of ones that we can find. So we can take a look at this. We know what that was from before, but we can also group these 4 together. So let's see what that ends up being. Well, on the original one, remember if we look at the middle square where we have all those 4 ones, A is transitioning, okay, and C is transitioning from 0 to 1, so it's just B. Now, how about in this case here on the left, or on the right rather? All of these are 1 in this column. Okay? And if you look at it, though, from any one of these combinations going from top to bottom on the rows, everything is transitioning for A and B. There's no case where they're the same. But C in this column, they're all 1s. So we would write that as B or C. That would be the total circuit. Now it's kind of interesting. What happens is both A and D completely fall out of the equation. They become irrelevant. They don't affect the circuit. Let's go through a couple other quick examples. Okay, let's do another example here. Kind of like doing Sudoku, but not really. So I've created another truth table here of an example circuit, and we have 0, 0, 0. A, B, and C are 0, so we have a 1 there. 0, 0, 1 is a 1. 0, 1, 0 is a 1, but 0, 1, 1 is 0. Next row, 1, 1, 0, right here is a 0. 1, 1, 1 is a 0. 1, 0, 0 is a 1. And 1, 0, 1 right there is also a 1. Now in this case, again, we want to group the maximum number of 1s together. So you might think, first of all, well, we can do these 4 and these 2. But we can do a little kind of a trick here. We can do a little overlapping. We can do this set here, like that. And then we can take these 2 and group them with these 2. Kind of weird. You can't group 6. It's not allowed. We're always doing everything in powers of 2. So let's take a look at these 4 on the top to begin with. A is 0 as we go from top to bottom. So that means the term would be A naught. C is transitioning from 0 to 1 on those cells, so we throw it out. Now this is the weird one, where we've got this transition, and let me erase it a little bit to make it a little bit more clear. Okay, so the way you have to kind of think of that, you think, well, those don't look like they're adjacent, they're on the top and the bottom. But again, kind of visualize it as a piece of paper that's kind of curved around on itself. So there can be adjacency from top to bottom in this case. So what we're going to do is look at each letter, each variable input, and look and see if they're changing or not. Okay? So if we go from this row here to this row here for A, it goes from 0 to 1. So we have to throw it out. B, however, if we go from this row to this row, it stays 0. What does that mean? That means B naught, okay, because it's a 0. And here, if we look left to right for these 2 sets here, okay, C is changing from 0 to 1, so that means we throw it out. So what this ends up being is A naught or B naught. Okay, let me give you one more example here. Okay, I hope you caught that mistake. I just realized it, and I'm not going to try to fix the video here. But what's the mistake? I've got 6 1s here, but how many do I have in my column here? I've only got 5. So I had a mistake here. This 0, 1, 1, which is 0, 1, 1 here, should have been a 1. So this should have been a 1 here. So sorry about that, but trying to re-edit this is getting to be a pain, so I'm just going to try to forge through it. So hopefully that didn't throw you off so much that you threw in the towel. Okay, let's look at the next step. Okay, last example here for these 8 input Kmaps. And by the way, yes, we'll get into 4 input. They end up being a 16 cell matrix. So let's take a look at this one here. So again, we're going to try to group with the largest number possible in powers of 2. But there's only 2 here that we can really group. We can group this one, and we can group this one. Okay? So A and B are both 0 as we transition from left to right. So that means what? If they're both 0, they have to be inverted. So that'd be A naught, B naught. And then going on, and C is transitioning from 0 to 1, so we throw it out. Here, A is transitioning from 0 to 1, so we're going to get rid of it, going from top to bottom. B is 1, so we write a B here, or B. And how about C? C is 0, not transitioning between that cell and that cell. So because it's 0, though, we would write that as C naught. Okay, I think that's enough examples for now. We'll probably get into some of the larger Kmaps in a bit.